We are now on chapter 10, simple harmonic motion and elasticity, and we'll be defining what the ideal spring is. Fx is the applied force, k is the spring constant here, and this is the x where how much is displaced. Okay, so look at this one. Well, before we move on to the picture, we'll be defining Hooke's law, which is Fx equals negative k x time, and this is the restoring force, and this moves without any friction. So it's a frictionless motion. That's what we call as simple harmonic motion. Now look at this. It shows you clearly the expansion of the spring, and when we apply the force otherwise, it goes back to the normal position here or squeezes back. So this is how is a clear picture of what that is. This is a very important topic here, simple harmonic motion and the reference circle. You can look figure 10.8, 10.9, and the displacement is defined here as x equals a, which is amplitude times cosine theta, and theta is omega times t. So you have, as you see here, omega is 2 pi over t. F is the frequency, then is 1 over t is the period, so t actually is the period. You can refer to figure in the page 255. Okay, so I can show you that better here. Look at this. We have attached a pointer to this spring, and the paper roll unfolds, it moves down, and slowly you will find a graph like this, which is a sine graph. Here you have time period and amplitude both defined. Now this is a form of simple harmonic motion. As you see, we have so we already defined the displacement, as you know. We did that in the previous page. And here is the amplitude, which is going up is positive, going down is negative. T is the period, and this is from one cycle. From here all the way goes like this, top, coming back. This is one cycle. And the period T is the time for one complete motional cycle. Now we are moving to the next page, where we'll be defining the velocity here. So all this is out of a circle, that's why it is known as reference circle. And velocity is tangential velocity, Vx is the regular velocity here. So Vx equals negative Vt sine theta, which is Px equals negative amplitude omega times sine omega t. This is in motion, so V tensile will be negative amplitude times omega. Then we'll be defining acceleration here. Ax equals AC. This is centripetal acceleration, and cosine theta, so same way, A omega square cosine omega t. So finally you have Amax equals A omega square. You will have a better idea when you will be looking into these pictures here. This is your film, and as you saw in the previous picture, here slowly the film goes down and it oscillates, simple harmonic motion. So you trace a curve which is sine curve, and there are light bulbs attached to it. This is your film here. So we are using this as a circle, and then from here you could see how to calculate displacement, how to calculate velocity also. This is for the velocity. It's a very clear picture. Here we have tangential velocity and regular velocity all in this little triangle here. You can look at this yourself, it's not hard to understand. This page I am showing you how we are going to calculate the acceleration from tangential and centripetal. We are relating acceleration A with the ball's shadow, x component of the centripetal acceleration AC, and ball on the reference circle. Okay, we'll be defining the work done and energy, where work done is F cosine theta times displacement here. Then finally we go on simplifying. So the difference between initial elastic potential energy and final potential energy will give you the energy PE total, which equals half kx squared. This is in joules. So please go over example 7 on page 261. Here comes the example of simple pendulum. This angle has to be less than 10 degrees. It oscillates one side all the way, back again, to and fro, and finally it comes to rest in the center. As you see here, the weight mg will be acting here and the tensile force will be acting on the other side. It is similar to the film and how the graph is drawn. There is one simple equation in pendulum where you have omega equals 2 pi f under root g over L, and this is only valid for small angles, as I said. And this is the length of the pendulum. Now, next topic we have is the elastic deformation, where we'll be relating the length, volume, and shear, all three different kind of modulus. Okay, the first is Young's modulus. Well, we are at Young's modulus now. F equals y, which is the Young's modulus. This is the constant. You have a table there, which is table 1. He gives you details of all the different y values. Delta L is the change in length over initial length. A is cross-sectional area. And mostly you will be using table 1 to solve problems. Now, shear modulus is something like this. Let's say you have a book. You are applying force on the top. The bottom layer remains the same. It slides layer by layer. So this is an example of shear modulus. And we have also one equation here. And that equation is referring to figure 10.9, page 269. F equals S, the constant for shear modulus, which is proportionality constant. Then you have delta x over L0 times cross-sectional area. There is another table 10.2 which will give you different values of shear modulus. And bulk modulus deals with pressure. Now look at P equals F over A, where P is measured in Pascal and the bulk modulus is delta P, change in pressure, equals negative B, which is the bulk modulus constant, delta V over V0. So delta V is change in velocity and V0 is initial volume. I'm sorry, not change in velocity. It is change in volume, which is delta V divided by V0, which is your initial volume. Then we have the last topic here. We'll be relating stress and strain. Look at this table 10.4 on page 271. Stress is directly proportional to strain, or strain is directly proportional to stress, which is figure 10.23, page 272. This is how your original volume was. Change in volume applying pressure all through, right, left, top, bottom. Now look at this equation we have. Okay, first equation you have force divided by area equals Young's modulus Y, delta L divided by L0. Then we have for S, which is shear modulus, delta X over L0 times this constant, which is shear modulus, and bulk modulus is here which is delta P, change in pressure equals negative delta V over V0. So as you see, stress on the left side all proportional to the strain. This is all about chapter 10. So here we talked about simple harmonic motion and what are the three types of deformation: length, bulk, shears, and also simple pendulum. Simple pendulum is the lab experiment you will do, or write a lab report later on as per the schedule wise. And spring constant K also you will be doing a similar experiment, not sidewise but going vertically up and down on the y direction, and measure the period